All right, so you've sent in some really interesting stuff about functional notation and trig functions. And today we're going to take a deep dive into, how these mathematical tools can be used to describe relationships and, importantly, how we can change or manipulate them using transformations.
Yes.
I've got a bunch of great excerpts here with definitions, examples, and a rundown of all the key transformations.
Yeah.
By the end of this, you're going to have a way clearer and hopefully more intuitive sense of how functions, both your standard algebraic ones and those wavy trig functions can be changed, both visually and conceptually.
Yeah.
So functional notation.
Yes. Functional notation at its core is really a very concise way of expressing a mathematical relationship. For every input you put in, there is a corresponding output that's determined by a specific rule. So this f of x notation, with x being the input, and f of x being the output, is so powerful because it really highlights this dependence. It's the language we use to describe how one quantity mathematically relates to another. And it's really the foundation upon which our understanding of transformations is built.
So it's like a process.
Yeah.
Feed in an x, the function f does its thing, and then out pops f of x.
Exactly.
And understanding that basic input-output idea is key to understanding what happens when we start tinkering with the process itself or with what we initially put in.
Exactly.
So that leads us directly to transformations of a basic function, f of x. So let's start with reflections.
Right.
What is the effect of reflecting a function over the y-axis?
So reflecting over the y-axis is like taking a mirror image of the function across that vertical line. And mathematically, this happens when we replace x with negative x within the function, resulting in f of negative x. What's interesting here is why this creates a reflection. For any point xy on the original graph, we now have a corresponding point negative xy. On the transformed graph, the y value stays the same, but the x value flips its sign, mirroring it across the y-axis.
Right, it's like a perfect mirror image.
Exactly.
And the example from our sources where f of x equals x squared becomes f of negative x equals negative x squared, which is also x squared.
Right.
It's pretty interesting.
Yeah, it shows. Functions like these, where f of x equals f of negative x, which are known as even functions, they have this inherent symmetry about the y-axis. It kind of gives us a clue about the nature of the relationship. It's balanced around that central vertical line.
Okay, so now let's flip it the other way.
Okay.
Reflecting over the x-axis. What's going on there?
Okay.
So that's where we take the whole graph, and we flip it upside down or right side up. The transformation for this is negative f of x. So when we start with f of x equals x squared, then negative f of x becomes negative x squared. You can immediately see how all the positive y values become negative, and vice versa.
Exactly. So each point xy on the original function now corresponds to x negative y on the transformed one. It's a vertical flip mirroring across that x-axis.
Okay, so we've talked about reflecting.
Yeah.
Now let's move to shifting. What happens when we start adding or subtracting values, either inside or outside the function? So let's talk about horizontal shifts first. So horizontal shifts are about moving the graph left or right. And this can sometimes feel a little counterintuitive.
Yeah, it can.
When you have f of x plus a, where a is a positive number, the graph actually shifts to the left by units. And conversely, f of x minus a shifts it to the right by a unit.
It's that counterintuitive aspect because to achieve the same output value as the original function at a particular x, you now need a different input value. So for x plus a, to have the same output that f of x had at, say, x equals 0, you now need to input x equals negative a. So you're essentially compensating for that added a by shifting the input. So the example of f of x plus 2 shifting f of x 2 units to the left perfectly illustrates this adjustment of the input. And similarly, for a shift to the right, you need a larger input to get the same original output.
Okay, so now what about moving the graph up or down, the vertical shifts?
So those feel a bit more straightforward. If you have f of x plus a, the entire graph slides upwards by a unit. And if it's f of x minus a, it slides down by a unit. Every y value is simply increased or decreased by that amount. So f of x plus 3, shifting the graph up by 3, is a clear illustration of this. Direct effect on the output. each point xy on the original graph moves to xy plus a for an upward shift, and to xy minus a for a downward shift.
Okay, so let's talk about scaling next,
All right.
specifically vertical scaling. So vertical scaling involves multiplying the entire function by a constant, let's say giving us a times f of x. And the effect of this depends on the value of a.
Yeah.
If the absolute value of a is greater than 1, it stretches the graph vertically, pulling it further from the x-axis. If the absolute value of a is between 0 and 1, it compresses the graph vertically, squashing it closer to the x-axis. But the sine of a
Yes.
also plays a critical role, doesn't it?
Absolutely. If a is negative, not only do you get the stretch or compression, but also a reflection across the x-axis. So for instance, 2f of x would double that distance, while negative 0.5 f of x would have that distance and flip it upside down.
Okay, so we've covered flipping, shifting, sketching, squashing. Now there's one more key transformation here in our sources.
Okay.
The inverse function. And this feels conceptually a bit different from the others.
It is distinct conceptually.
Yeah.
The inverse function is essentially about undoing the operation of the original function.
Okay.
If our initial function takes an input x and produces an output y, y equals f of x. The inverse function ideally takes y as the input and returns the original x. Mathematically, we represent this as x equals f of y. And to find the equation of the inverse function, we swap x and y in the original equation and then solve for y.
So in the example where f of x equals 2x plus 1, we swap x and y to get x equals 2y plus 1, and then solving for y gives us y equals x minus 1 over 2, which is the inverse function. So graphically, what is the connection between a function and its inverse?
So graphically, the inverse function is a reflection of the original function across the line y equals x. And this reflection happens because we've swapped the input and output roles. Every point AB on the graph of f of x will have a corresponding point BA on the graph of its inverse, hence that symmetry, across the y equals x line. So it visually represents that undoing of the function. The outputs of the original become the inputs of the inverse and vice versa.
All right, so that gives us a good grounding in functional notation and those core transformations. For general functions, now our sources also delve into trig functions. And these seem to have their own characteristics with their angles and repeating patterns.
Yeah, they do have their own unique properties, but it's fascinating to see that these same principles of notation and transformation that we've been discussing are still completely applicable. So trig functions like sine, cosine, and tangent, they relate angles within right triangles to the ratios of their sides. What makes them particularly interesting is their periodic nature. Their values repeat at regular intervals, which gives us those wave-like graphs.
Right. So you have the sine function, which is the ratio of the opposite side to the hypotenuse, and its graph oscillates between -1 and 1 with a period of 2 pi. And there's cosine, the ratio of the adjacent side to the hypotenuse, which looks a lot like sine, just shifted over.
Exactly.
And finally, tangent, opposite over adjacent, which is periodic, has a period of pi, and has those vertical asymptotes where the cosine value is 0. So those are our basic trig functions.
Yeah, the foundation. And when we apply transformations to them, you'll see some parallels to what we talked about with f of x. So let's start with amplitude. Changing the amplitude in a trig function, like sine or cosine, involves multiplying the function by a constant, let's say a, giving us a sine x or a cosine x. And this scales the height of the wave, which is just like vertical scaling for general functions. So if you have 2 sine x, the amplitude becomes 2, meaning the graph reaches a maximum of 2 and a minimum of -2.
So the value of a directly controls how much the graph stretches or compresses, which then controls the amplitude. Which is that maximum displacement from the midline of the wave.
Now how do we change how often the wave repeats itself? The period.
So that's achieved through transformations like sine of bx. The period of this new function is 2 pi. Divided by the absolute value of b. So if b is greater than 1, the period becomes shorter, meaning the function oscillates faster. For instance, sine of 2x has a period of pi, so it completes 2 full cycles in the same interval as sine of x completes 1.
So it's like squeezing more waves into the same amount of space. Exactly the b value, essentially. Compresses or stretches the graph horizontally, impacting the frequency of the oscillations.
And we can also shift these waves horizontally, which is called a phase shift. And in our notation, that's sine of x plus c. So this shifts the function left if C is positive and right if C is negative.
Yeah.
Just like those horizontal shifts we saw with f of x.
Exactly.
And that example assign of x plus pi over 2 being a shift to the left by pi over 2, but actually being equivalent to cosine of x really shows how these transformations can connect the different trig functions.
It really highlights that interconnectedness within the family of trigonometric functions. And lastly, just like any function, we can also apply a vertical shift. Just trig function.
Yep, so something like sine of x plus d.
Right.
This simply moves the sine wave up by d units if d is positive and down if d is negative.
Yeah.
Just like the vertical shifts for general functions.
Exactly. So that underlying logic of the transformation remains consistent.
What's really cool is that these core principles of functional notation
and these transformations that we've been exploring, they apply seamlessly to trig functions.
Yes.
So whether it's a reflection, a shift, or scaling, the way that we modify x, or the output of the trig function, has the same kind of effect on those wave patterns.
So by understanding these transformations, you gain a powerful analytical tool. If you have an equation like 3 sine of 2x minus pi plus 1, you can immediately start to dissect what its graph will look like, a sine wave. That's been stretched vertically by a factor of 3, compressed horizontally by a factor of 2, shifted to the right by pi over 2, and then shifted upwards by 1. You can almost picture it without needing to plot individual points.
That's the power that it gives us. It lets us predict and analyze mathematical relationships. You can take what looks like a really complex function, and just by recognizing these transformations, you can understand its behavior and its graph.
It gives you so much more intuition than just memorizing. A collection of graphs.
So to wrap up our deep dive today,
we've explored how functional notation, that fundamental f of x language, really helps us describe mathematical relationships. And we've looked at how applying specific transformations, reflections, shifts, and scaling to a function's equation directly changes its graph, both for general functions and for trig functions.
What's important is we've seen that these aren't isolated concepts. The same principles govern how these transformations work across different kinds of functions. Understanding these tools gives us a much better, less formulaic way to visualize and analyze mathematical expressions.
It lets us go beyond just plugging in numbers and hoping we get a recognizable shape to really understanding how the equation creates the graph.
Exactly.
So here's a final thought for you.
Okay.
How could we use these transformations to analyze patterns in the real world, like sound waves or seasonal cycles or other things you might see in data analysis or science?
It's about learning to see that mathematical structure and how those changes in that structure show up in the real world.
Well, thanks for taking this deep dive with us today, and thanks for sharing your sources with us. It's always great to unpack these fundamental mathematical ideas